Recording in progress. If you keep talking, and then I can record your voice, and then the students can listen to your private talks. Okay, let's get started. Maybe we can talk about their weekends later. And today we are going to move to another chapter. It's about approximating the new chapter here is about approximating to the eigenvalues. And actually with the first method, you can also approximate the eigenvectors as well. So this is a new chapter, and we just get rid of that gradient descendings and move to the approximating eigenvalues. In case that you forget what is the eigenvalues, I will give out the definitions here at first. So first of all, if you forget, let's recall what we have for the definition of the eigenvalues. We have here we have a n by n system, n by n matrix of A, n by n matrix A, and we can construct a characteristics polynomial, and that's the determinant of the A subject the lambda times the identity matrix. And if we find out all the zeros for this characteristics polynomial, and that is the zeros of this characteristic polynomial are the eigenvalues, and that's the definitions of the values. And this is the definitions of the eigenvalues. And for the eigenvalues, we actually have the eigenvectors, the corresponding eigenvectors, and these zeros of the characteristics polynomial, they have they have the eigenvectors, and then it equals and it satisfies the following equation. And so if we have the eigenvalues and then we got the corresponding eigenvectors, and this is the eigenvectors, and these are eigenvector, and this is the eigenvalue. And there's some things before we move to the approximations algorithm for the eigenvalues, we would mention something related to the eigenvectors eigenvalue first. So I just show you the result. I'm not going to prove it, and you don't need to prove it as well, but I just show you the result, and then that is something we use to derive the algorithm. And I think this is something taught in the linear algebra class. And this is the 309.5 on the textbook. And it's stating that if a matrix A, this is a matrix, and it has the eigenvalues. Lambda 1, lambda 2, and then all the way to the lambda n other. But here we have one special thing here, are distinct. So sometimes the eigenvalues could be lambda 1 equals to lambda 2, and then the other things could be different. But here we require that in this theorem, the conditions for the eigenvalues are for all the eigenvalues here, they are different from each other. And so we have, they are distinct eigenvalues So maybe we can just have lambda k, although the A is n by n matrices, but if we choose the lambda 1, lambda 2 to the lambda k, that are the distinct eigenvalues from those n eigenvalues, and then we collect the eigenvectors, the associated eigenvectors together, and then they have these eigenvalues are associated with eigenvectors below. X1, let me just use V1, V2. V1, V2, and then to the Vn. And they are the eigenvectors corresponding to the lambda 1, lambda 2, lambda 3, and all the way to the lambda k. They are the corresponding eigenvectors. Then, if we collect these eigenvectors, and then we got V1, V2, and then to the Vk, this is a set of linearly independent set. So there's a remark here. So A is MIN matrices, and you probably have n eigenvalues, and then there are some repeated eigenvalues in it. But we just pick the distinct eigenvalues and collect the associated eigenvectors together, and then this set is linearly independent. So here we just choose the distinct eigenvalues together and collect them together. It has n eigenvalues, but we collect the distinct eigenvalues. Okay, got it? And this is the 309.35. And I'm going to give you some examples about the eigenvalues and eigenvectors in case that you forgot how to get the things. So there's one example, and then it's example 3 on the textbook. And we have the matrices. It's a 3 by 3 matrix, 2, 0, 0, 1, 1, 2, 1, -1, and then 4. And we are going to calculate the eigenvalues and eigenvectors. I'm not going into the details, but I just want to take a look to eigenvectors corresponding to the distinct eigenvalues, and then they can form a linearly independent set. But if you forget how to get the eigenvalues and the corresponding eigenvectors, you can go back to your linear algebra class to take a look. So first of all, we have, or you can go back to take a look at the examples 2 on the textbook, but it's on of the sessions 7.2, and there's some details process there to teach you how to get the corresponding eigenvalues and eigenvectors. So first of all, for the eigenvalues, and then you can just calculate the determinant of the A minus lambda I, and then you would get the characteristics polynomials. It is just after the factorization is lambda -3, lambda -2 and square. You will see here the lambda. There are 2 eigenvalues here, and then the first one is the, if we solve the p lambda equals 0, and then we get 2 roots here. The first one is 3, and then the second one is 2, but the 2 is repeated twice because we have the order of 2 in the lambda -2 to the order of 2. And so here we are going to, if you substitute the lambda 1, if you want to get the AV1 and then equals to the lambda 1 V1, if you want to calculate the eigenvectors V1, and then you need to substitute the 3 back to this eigenvalue eigenvectors equations here. And then if you substitute the 3 back to here, then you will get the V1 vectors. If you substitute the 2 into AV2 equals to lambda 2 V2, and because this one are repeated, and so you might expect that you would get 2 eigenvectors for that lambda 2 dimension. So not really. So you just get 1 eigenvectors for the lambda 2. So let's see. So we have corresponding to the V1, the lambda 1, and then we have the V1, and then the V1 is just the 0, 1, 1, and then I use a transpose here because usually we are representing their vectors in terms of column vectors. And if we substitute the AV2 and then lambda 2, we substitute the lambda 2 into this eigenvalues equations, and we might get the, yes, we might get 2 eigenvectors, and then they are corresponding to the lambda 2. And then we got the 0, 2, 1, and then that's transpose, and then V3, and we got the, let's see, and then we got the negative 2, and then 0, 1, and then transpose. That's quite interesting here because we have the lambda 2, actually we have this 3 bases, these 3 vectors here, that is, these are eigenvectors. And but these 2 eigenvectors are corresponding to the lambda 2. But actually you find that these 3 eigenvectors are linearly independent. It's something different from what we have mentioned in the theorem. And these vectors is corresponding to the same one, but if we collect them together, and then they are actually linearly independent. So if you want to calculate, prove this are linearly independent, and then you could say, you could. So I would give you the idea to prove they are linearly independent. This is something related to your homework 1, and then you would just say, okay, we have the vector z, and then let it to be c1 v1, c2 v2, and then plus the c3 v3. And what you are going to do is to prove the c1, c2, c3 equals to R0s. The idea is to do the inner product with the z, and then you check the inner product with v1, and then let it to be 0, because here the z we set it to be 0, and we want to prove the c1, c2, c3 equals to 0. And the second step is taking the inner product with v2, and then z, taking inner product of the V3, and you will find out that from this one, C1 equals to 0, and then from this one, C2 equals 0. From this one, the C3 equals to 0. And this is the idea how to prove them, prove these vectors are linearly independent. So this is the idea to prove, and then V1, V2, V3 are linearly independent. Linearly independent. And so this is the example, although the vectors, 2 vectors here are corresponding to the same eigenvalues, and then but now this set of the vectors are still linearly independent. But let's take a look at the next example to see So here, if we collect these linearly independent vectors together, and then that could form a basis of the dimensional three dimensions space here, because they are linearly independent, and then we have three vectors here, so they can form a basis of the R3. But let's take a look at another example, and then that's again a 3x3 matrix, and it's the example 4 on the textbook, and then that's the matrix 2 1 0 0 2 0 and then 0 0 3. And once again, we can go to get the characteristics polynomial, and you'll find that's quite interesting. These two examples are quite similar, but this is A minus lambda I. And then we have the same characteristic polynomial here. Let's see, what is the first one? The first one is just 2 1. They are different matrices, but they have the same characteristic polynomial. And if we go to solve the zeros for the characteristic polynomial there, and then we get lambda 1 equals to 3, again lambda 2 equals to 2, and then these eigenvalues are repeated. And if we want to solve for the vector 1, so once again, we want to solve for the eigenvectors, and we would have a v1 lambda v1 and then lambda 1 v1, and we just substitute the lambda 1 equals to 3 to that equation, and we just substitute this one to this equation, and we solve for the v1, and the v1, if you keep solving the things, and then what do we have? We have, let me see, we have this. We have the eigenvectors is 0 0 v1 equals to 0 0 1, and then do the transpose because this is a column vector. This is eigenvalues with just all the ones, so we just have one eigenvectors. And then let's see for the AV2, and then what can we get? AV2, and then we substitute the lambda 2 equals to 2 here, but this is another matrix. We are working on the B matrix, and then B matrix. And we do the substitution here. Actually, we can get just, if you do this solving process here, and so for the V2, you will find out that this lambda 2 is just corresponding a one-dimensional eigenvector space, which means that the V2 is only in tensor. So the V2 is just the 1 0 0 transpose. And let's compare this to example. So for the example 1, the lambda 2 is corresponding to different directions eigenvectors. That is the V2 and V3. But in this example, although we have the same eigenvalues, the values is the same. But here, although the 2 is still repeated, but for this examples, we'll find out that the eigenvector space corresponding to the lambda 2 equals to 2 is just a one-dimensional space here, and then which means that there's just one eigenvector corresponding to the lambda 2. Does that make sense? So you can see the difference here. We have the same eigenvalues, but here, if you take a look at here, if we collect all the eigenvectors, if we collect all the eigenvectors, and then the eigenvectors are just V1 and V2. And yes, they are linearly independent. And this is quite obvious because the V1 cannot you cannot use any linear combination of V1 to represent V2, and on the contrast way, and then you cannot represent the V1 with the linear combinations of V2, and so they are linearly independent. But we cannot use this set of the vectors to represent to use this set of vectors as the basis of the R3 because but we cannot use this set of vectors as the basis of R3 because it's quite obvious, because the vectors 0, 1, 0, and then this vector is not a linear combination of the V1 and V2. Okay, any questions by so far? So I give you 2 examples, but in these 2 examples, and then we could find out that the eigenvectors corresponding to the different eigenvalues, distinct eigenvalues, they are linearly independent. But if you get the eigenvectors and then the number of the eigenvectors that is less than the dimension, then we cannot use it as the basis of that space, the n-dimensional space. And this is the examples we get. Any question? Any questions? No? This is just some things from the linear algebra, but I just give you 2 examples to explain the idea in the theorem. But sometimes for the repeated eigenvalues, sometimes you would get different dimensions, different directions eigenvectors as well. So this is example 3 and 4. And next, I'm going to introduce some things we would use in the next class, and then that's the similar idea, the similar matrix similarity idea. So first, I'm going to define. So the next part is about the similarity. And first, when I am talking about similarity, and then we need to define one matrix, and let's see, this is the definition, and we say that Q, so the definitions of orthogonal matrix, in case you forgot what is the definitions. So Q is orthogonal, and if, so you will see some definition here, and you need to be very careful. If it's columns, the columns of the matrices, we have, let's say the Q is n by n matrix, and then we have the Q1, Q2, and then Qn. And these columns formed an orthonormal set in the Rn. And you'll see there's something very weird here. So we require that the columns to form an orthonormal set, and then we call this Q is orthogonal. Okay, good. And let me see. Let me remind you something. And what is the orthonormal mean? It means that we require that the Qi, Qj, the inner product of them equals to 0. If the I does not equal to j, and the qi equals to 1. And this is the two requirement for orthonormal. And this is the definitions of the orthogonal matrices. And I'm going to show you some property for this kind of matrix. And let's see, this is, you don't need to know how to prove it, but if you are interested in the proving, you can go to take a look at the linear algebra book. So suppose the Q is an orthogonal matrix, n by n matrix. And then we have the following properties. So first, the Q is invertible. And there's one beautiful property about the inverse as well, invertible. With the Q inverse equals to Q transpose. So which means that the Q inverse is pretty easy to calculate. You just do the transpose, which means that you just need to switch the positions. And the second one is the inner product is something about the inner product. So for any x and y in the n-dimensional space, you have the qx transpose and then qy, and then equals to x transpose and then times the y. So which also means that, so let's see, what does it mean? It means that the qx, so inner product with the qy, and then equals to inner product of the x and y. And this is the another format of this property. And let's see. So 3. And the 3 is about the, so for any, this is something from the property 2. If you get the y and then take the y as x, and then you would get this. So for any x in the Rn, the n-dimensional space, and then the qx, the 2 norm equals to the x2 norm, which means that after the transformation, and then you are not changing the norm of the vector. Could you give me one examples of the Q matrix? Identity, yes, you're right, because it would not change that norm of the vector, right? And I'm going to, are you answering the questions? Do you have any idea?
Or just the Q matrix?
Yeah, the Q matrix, do you have any?
Consists of the eigenvectors.
The eigenvectors, yes, eigenvectors is also one of the one things to form the Q matrix, because the we can require that the things are orthonormals, because you can normalize the eigenvectors there. One of the things, another interesting examples about the Q is, so identity matrix is good. So which means that after the transformation, this is the x vector, and then you are going to keep the x vector, and then that is the same one. And yes, you're right. But there's another examples for the Q, and then that's the rotation, which means that if you rotate the Q, the x here, maybe with some degree, maybe it's the 45 degrees. And then if you take a look at the length of the vectors, it's just the same, right? You're just doing some rotation here, and then it's not changing the length of the vector here. And so that you will see, usually the L2 norm and the n-dimensional space, especially for the two-dimensional space, and then the L2 norm is just the length of that vector. And if you are doing some rotation here, and then at the end, the length of this vector does not change. And Q if you write out the rotations matrix, it says the concrete format, and then you will find out that the Q is actually orthogonal matrix as well. So next, this is just one example. And there's one more things from the first one. The first one, we also get the Q. I'm going to do the multiplications on the both side by Q, and then I get Q, and then times the Q transpose equals to the identity matrix. Does that make sense? So I just multiply the Q on the both sides. And also there's one more things. If you go back to take a look at the definition of the Q norm, the matrix norm, it's just the Q, and then the Q, this norm is equals to the maximums of the X equals to the norm equals to the unit vector. So we are taking the maximums among all the unit vector, and then but it's related to the 2 norm, and then we have QX and then 2 here. So this is the definitions or one theorems about the Q2 matrix 2 norm. And if we use these definitions here, and you will figure out that, so here is just the X equals to 1, and then this is QX2. And then from this property, and then what's the norm of this Q2 norm, the 2 norm of the Q. So let's see. So this is some property when we define the matrix 2 norm. And then you are taking the maximums among all the unit vector, and then for this norm. And then this one is just QX, and then 2 norm equals to the X 2 norm, and then equals to 1. So here the Q2 norm is just that 1 equals to 1. And this is all the property we get for the orthogonal matrix. Okay, good. Any questions by so far? The property. And we might use these properties later on because this is all the things about the similarity. The similarity is, so I'm going to give you the definitions based on the orthogonal matrix here, and is the similarity. Okay, good. So definitions first. Definitions of similarity between the matrices. And so here we have 2 matrices. Let's say we have the 2 matrices, A and B, and they are said to be similar. And if n, if a non-singular matrix X exists, if this S matrix exists, and then with this property, with A equals to the S inverse BS. And this is the similarity, the definition of the similarity. And but here we just require this matrix S to be non-singular. But we have theorems and about the eigenvalues and eigenvectors as well for the similar matrices. And this is something we are making use of the property. This property we are going to use in the derivation of one of the algorithm later on. So this is very important theorems about the similarity. And that is the theorems 9.12. It's the eigenvalues and eigenvectors of the similar matrices. And eigenvectors for similar matrices. And actually they have the same eigenvalues and eigenvectors. So I'm going to give you the details statement here, but the idea is just the same. They have the same things. So suppose we have two matrices and then they are similar. A and B are similar matrices. And let's say we have the A equals to the S inverse BS, and then the lambda is an eigenvalue of A, and then with the associated vectors, eigenvectors with associated eigenvector V. Then, so the conclusion is that, so if the lambda is an eigenvalue of the A, and then the lambda is an eigenvalue of B, that is the similar matrix here, and this eigenvalue is with the associated eigenvectors. It's not exactly the same, but it's something's related to the eigenvectors we have above, the V matter, and then that is the SV here, which means that, okay, if we have the similar matrices here, and then they have the same eigenvalues, but for the eigenvectors, we have the eigenvectors for the A is just a V, and then the eigenvectors for the B is the SV, and then the eigenvectors for the B, and then we need to we also need the matrices for the similar transformations there, similarity transformation there. So this is the SV. Okay, so this is one theorem, and then we would use this theorem to divide the second algorithm for the approximations of the eigenvalue. And next, but we are not going to prove the theorems. We are just making use of this theorem to divide the algorithm. And next, so there's one more thing, and then that's very nice. So here by so far, we don't require the S to be to have any specific property, but for this corollary here is something about the similar matrix, where the similar matrix is the orthogonal matrix. So let's see. So first, there's a theorem here. So let's say the n by n matrices is a symmetric one. The n by n matrices are symmetric. And then if and only if there exists a diagonal matrix V and an orthogonal matrices with the Q and then the Q transpose. And then it's this one. And this means that symmetric matrix is similar to a diagonal matrix. And then the similarity, that's transformations matrices is an orthogonal matrix. Does it make sense? Because if you take a look at here, by the definition of the similar, it should be A equals to S inverse, right? D and then S. But here, let's define the Q as the A S inverse. And then, so the S should be the Q transpose. Does it make sense? Because we have one property here, the Q inverse is just the Q transpose. Okay, so this means that any symmetric matrix and then is similar to a diagonal matrix and with the transformations matrix to be an orthogonal matrix. And they have nice property here. And actually there's one corollary from the first theorem. And it's also, so this is the theorem 9.116. And actually we have one more corollary here is about the matrices. If the M, we have a M by M matrices here, A, and then that has n distinct eigenvalue. And they are similar to that diagonal matrix. And as the students who just mentioned before, and then you just mentioned that we can form a Q matrix, right? And then by the eigenvectors, right? And actually here we can form this eigenvectors and or the orthogonal matrix in this way. You just get the eigenvectors, normal eigenvectors. So we need to do the normalizations for the eigenvectors. And this is the M by N matrix, and then it's symmetric, and then they have their the n distinct eigenvalues, and then we can take the Q to be the eigenvectors, and but with the norm equals to 1. And then we connect all the columns together, and then that is a Q. And then the D is just the eigenvalues of the A. Any questions? So this is one way we can get the concrete expressions for the Q and D and Q transpose here. And I'm just writing down all the things here. So the Q could be, so remote, the Q could be the V1, V2, Vn, and the Vi here is the eigenvector, but we require this one is normalized. Normalized, which means that we get the if we calculate one eigenvector and then they are not with the norm 1, and then actually you can do the normalizations process, and then you define the new vector to be the Vi and then divided by the norm of the Vi. And this is the normalizations process, but so we require that in this set of the vectors, eigenvectors, and now we require the eigenvectors to be normalized eigenvectors of the A. And the D, on the diagonals matrix, and then the D is just the diagonal of. So I'm going to use the diagonal and then to create the matrices, and then on the diagonal it's just the lambda 1, lambda 2, and then to the lambda n. And so the lambda 1, the lambda I is just the eigenvalue corresponding to that eigenvectors Vi. Eigenvector Vi. And that's it. And this is the remark for the theorem 9.16. Any questions right so far? Questions? No? So if you don't have any questions, and then let's say there's one more things about the matrices and eigenvalues. So there's one more thing is about the matrices and eigenvalues. And this is some things you might already know. And symmetric matrix A is positive definite. And actually, we have already used this property in the 104B as well to decide whether a matrix is whether is positive definite or not. So this matrix is symmetric and then is positive definite if and only if. So if we just take a look at the eigenvalues of the A, and we want all the eigenvalues of the A are positive. And this is one more property about the eigenvalues and eigenvectors. Any questions here? And this means that if we have a symmetric matrix here, and then if this is a positive definite matrix, and which means that for the diagonal components here, they are all positive in the factorizations here, in the A similarity expressions here. Does that make sense? If you combine these two theorems together, and then you will take a look at, okay, if this one is of symmetric and positive definite matrix, and this means that this matrix is similar to one diagonal matrix, and then for all the diagonal components, which are positive. Okay, so I think that's all the, we just stop here, and then, but the next time, we are going to talk about the power methods, and then we are going to use the property and theorems we mentioned in today's class to create the powers methods. So the powers methods is quite simple. The idea is using some way and then doing the iteration and then give it AX and then an initial guess here. And then actually we are doing some detailed processing there, but you are going to do the multiplications again and again, doing the A multiplication, and actually we can denote this as the AKX. And then we are going to use this to approximate the eigenvectors. And then during this process, we are also approximating the eigenvalue as well. In the derivations of this algorithm, we would use the property we mentioned today. So you need to really take a look at the property we learned today and all the theorems we are talking about today. And that's all. Thank you.我下次应该 post 那个 note 先的，我还忘了先 post。
问是不是不一定是 LT 问？
这个不行，这个一定要是 LT 吗？因为你这是 define 那个 inner product 的那个形式。
什么意思？
因为就是我们怎么去定义这个 norm 的呢？就是这样子的 inner product。
就是你定义的这个 inner product 是吗？就是你定义的 inner product 这个，所以说是知道是。但是我意思就是说，它是不是换成别的诺也行？
啊？他们怎么在这边？哦，没有，你继续吧。
就是按理来说，它应该也可以是别的诺。
不可以，不可以。因为 infinity norm 它就是 take 那个最大的component 嘛。你看我是怎么打的？
我不是说这个 property， 我是说这个，因为
不能 QX 你说等于2等于 x 这个2吗？不可以啊。
就是 QX。
不能啊！不能啊！你没有这个，你怎么推导呢？我们这里定义的它是那个，因为它是那个 inner product 是这样子，有这个性质才会有这样子的呀。你自己想想哈，我问你哈，你过来看，好。 你想想哈，我们这个我不是 Q 说那个是可以是用 A 对吧？你想想这里最大的，如果你其实你在那地方，那不就是说最大的这个功能？最大的功能是等于一个，对吗？但是如果是这样子的话 ，x 的infinity norm 就是对吧？然后你做了 rotation 之后，不就 qx 吗？first 等于多少？square root 2，对吧？这样子 qx 的infinity norm 等于多少
Oh yeah, the conjugate rate.
？square root 2是不一样。
Conjugate rate.
我怀疑那个103和104的那个时候，它有可能我觉得它没有 subscript， 但是它那个 subscript 没有 subscript 的情况下，它默认是 L2 norm。我怀疑是这样子的。
然后我也在看。
Just the size of the
OK， 对。
What's the difference between the infinity norm and the actual norm?
The infinity norm and L2 norm. Have you learned that definitions? 没有学这个。
可能形成我忘了。
I don't know. I don't know. 它上面有这个呢L2 is 0 to 1。那它的不是我们只需要一个东西就有这个 norm。Infinity norm of this vector. Just taking the maximum of the component. 1, 2, 3.
Wait, L2 norm is like the square root of this square plus this square.
Yeah.
Oh, that's the L2 norm?
Yeah.
Okay, I learned that before. I just don't know that it's called L2 norm.
Okay.
We just call it norm.
Okay, but because in this class we have different types of norm. If you have take a look at the conjugate gradient methods, the examples we are using the infinite norm there
Yes.
because it's easy to calculate.
But basically, this is just to find like which component is the maximum error.
Yeah,
You want to know the maximum error for this whole approximation.
Yes.
Okay.
So, but in this case we have just mainly we have 3 types of norm, and then that's the infinity and L1 norm, and then the L2 norm. For the
What's
L1,
the L1?
the L1 norm of the vector, we are just talking about the vector, okay? And if for the vectors, and then the L1 norm is just the 1 plus the absolute value 2, and then plus the absolute value of 3, which means that this is the sum of the absolute value of the components. This is 1, 2, 3, right? And then you do the sum, but without that square.
Okay. Just to confirm, the L2 norm of this will be
Square,
1 plus
square, and then doing the square root.
Oh, okay. And then, for this, you mean like taking the inner product of
Yeah,
zero and the vector?
And that's how rather with the V1.
You
and
can
then-
prove either this or this for linear independence.
What?
You can prove either this, like C1.
So here, how to prove the C1, C2, C3 equals 0, and then that is what these steps. So for the first step, you do the inner product with this, and then you will get C1 equals 0. Yeah.
So you prove this to get this.
Yeah.
Okay.
Not prove this. This is the things you need to do for each step. So for the first step, you are taking the inner product Z, and then with the V1, and then you are going to write something here, and then to say this is C1 equals 0.
Okay.
And then for the step 2, you would derive, you would get the result C2 equals 0. And then for the step 3, and then you would get the C3 equals 0.
Yes, and then another thing is for this one here, if the number of linear independent eigenvectors is less than n, like we have n-1, then this set of vectors
Cannot be the
create-
basis, yeah,
cannot be-
because the basis should be, the number of bases should be n.
Okay. And last thing is for this one, is this right? For orthonormal?
Normal, I don't have an A here because this is just a normal orthonormal.
So it's QI
Yeah,
equal 1.
equals 1
Okay.
because it's not A orthonormal.
Okay. Thank you.
Mhm. 嗯，
那天下午出去之前，您发给我的 V 图，
对
然后
你看
看完
吗
了。
看完了你和我讨论吧，你
对
找个时间。
我就是想什么时候看您合适，我是比如说明天 office hour，还是说另外找时间
另外找时间你发个 email 给我，不要是星期五下午就行。
？OK，
OK。
好的，谢谢你。
Office hour， 因为 Office hour 应该没有时间照顾到你，所以就是你要就另约一个时间。
OK，
好的。
除了周五下午都 OK，
什么？
除了周五下午都 OK。
明天周二的下午也不太 OK，周三吧。
Homework. Do we have to be in a group? Or can we be
You
ourselves?
can be a group. Yeah, you can just finish the things by yourself.
Okay, then I know on Canvas there's a group section doing to sign in without just submitting without joining any groups.
Which means, what is that meaning?
Like when I click on 我点开那个作业的时候，它上面写着说，如果你要 submit 的话，这个 submission 代表你整个 group。然后 Canvas 左边不是会写什么 syllabus modules 那一条吗？那一条里面有一个 tab 是写着 people， 你点进去 people 之后，会有全班的人在那里，然后又有一个选项写着 group， 你就可以点，你就可以 join 那个 group， 你知道吗？
你可以 join 对吧？
对，
我不知道，
你不知道？
不知道。那你
你
就可以
之前弄过 group coding
没有？
哦，
我没有在 Canva 上面弄过，我之前都是在另外的 Grayscale 上面弄过。
哦，
你给我看看。是这样子的话也可以。
它是你是 assign group。
对啊，你们
我先点开这个 coding， 它这里会说 ，Keep in mind this information will count everyone in your group setting. So 我点开 people 的话，这是全班的人嘛 ，everyone， 全班的人都有 groups， 然后你可以点 join， 就比如说我跟你 join 的这个 group， 我就在这里，然后我交作业的时候，
他能看到哪个 group 是谁吗？
应该是可以，我印象里是可以，但我不
不是
确定，
你看不到谁，但是
因为现在没有人在。
哦，印象中你是可以看到名字在这里的。
我记得是，就是你点 join 之后，或者是我只能看到我自己的组，别人看不到，但我不记得了，好像没有弄过这个东西。
我下次星期三课看看你们是怎么搞的。找多几个学生来试一下。
所以可以自己做。
肯定哦。
那我就不 join 就直接交了。
这么厉害的吗？
不是，因为我以前跟 project 都是我自己做。
对啊，是有这样子问题的，就是有。
所以我就不太喜欢。
就我也挺讨厌，我就是怕一些同学他不会做，所以说你们可以要有 group，然后 maximum 是 3，但是你们可以一个人。
哦。
对。因为，我之前也处理过很多这种情况，我烦死了，3个人，然后只有1个人做。
啊，对呀。然后那个2个人还得分。
没有。我主要是那时候，如果我接到投诉，我会 investigate， 很浪费时间。investigate 之后，我就要把给0分给那2个人。这个东西比较恶心，所以就全靠大家自觉。对，我觉得就是大家不想有个 group 的1个人也行，我觉得很恶劣。我只是怕有些同学他能力比较差，连 coding 都不会，只能抱大腿。我觉得这门课不走 coding 吧，因为。
我之前在 class 那节课上课吧，看了他的 A 和 B， 他说是我走 coding， 所以我 coding。他的 basic 他不要。
然后我觉得你们，而且就。